Hi, I'm Bárbara Tavares.
Hi, I'm Cécile Desforges.
Hello, my name is Juan José, and we are students from IFP School of the Processes and Polymers program.
In this video, we want to show you the importance of thermodynamic phenomena in a chemical process. But first, why you need a chemical process? Because in our daily lives, we are used to handle with several products and materials. But we never stop to think about the industry behind these products and how they are manufactured. So, for example, if you think about products as inks, varnish and adhesives, we never were curious and ask ourselves, what are the compounds inside the ink or adhesive and how they are produced? So, the idea of this video is to explain in the easiest way how a chemical process is made and what are the thermodynamic issues that we need to overcome in order to produce a solvent that is a main compound in order to produce a varnish or ink, for example. So, this solvent is the isopropyl acetate, or in the simplest way, IPAC. In the following video, we will explain how to synthesize IPAC, which are the steps for the separation and purification of this compound, and which are the problems that we need to overcome in order to produce it industrially. The first step to produce IPAC is the chemical reaction. The chemical reaction is when we have several molecules and these molecules will interact. Due to this interaction, will occur the formation and destruction of the bonds that you already have in the atoms. So, when you have the formation of new bonds, you form new molecules. So, a chemical reaction can be compared with a color mixing, for example, when you have blue color with yellow color and we form a green color. To the blue and yellow color, we can call it reactants because are the two ones that will interact in order to form the green. To the green color, we can call product, that is the result of the interaction between the reactants. Now, making the comparison with IPAC production, we know that we have two reactants that we need to produce IPAC, the isopropyl alcohol and the acetic acid. With these two compounds, when they interact, we obtain two products, the principal product, that is the IPAC, and a byproduct, that is the water. This reaction will lead to a dynamic equilibrium, but what is a dynamic equilibrium? A dynamic equilibrium is when we have a mixture of products and reactants and the quantity of these two remains equal. However, the reaction continues to occur, we have continuously formation and extraction of the products. So it's why we call a dynamic equilibrium. However, because we have a dynamic equilibrium, we can stimulate the formation of products by using two methods. The first one, we can remove some of the products that we have already in the vessel, or we can increase the quantity of reactants. In this way, we can favor the reaction in order to have more products in the end. Like this, we already know how to produce IPAC. Now the big problem is how we can separate the IPAC from the other compounds. We have products and more reactants. So the next step in this presentation is try to understand how we can separate the IPAC.
The most common method used to separate this compound is distillation. This technique uses difference of volatilities in order to separate compounds from a mixture. But first, we should know what is volatility. The volatility is a tendency of a compound to evaporate. The easier it vaporizes, the more volatile, as the A product in this example. So the separation takes place in the distillation column. However, during evaporation, there is entrainment of the heavier product in the vapor as well. This is why, in a distillation column, several equilibrium stages are used on top of each other in order to achieve an almost perfect separation of the A compounds at the top of the column, so-called distillate, and of the heavier product at the bottom in the residue. One can ask what makes that a molecule is volatile or not. As we should see, there is two different phenomena driving the volatility of a molecule, the bulkiness and also the stickiness. If we consider the first one, the bulkiness, it is related with the molecular weight or the size of the molecule. The lower the molecular weight, the more volatile the molecule is expected to be. So in the process that we are now studying, as we can see, the water has the lowest molecular weight. So as a first approximation, we expect that the water will be the most volatile compounds of the four. However, this is without taking into account the second phenomena, the stickiness. Here, the colorful drawing illustrates the electron density on the surface of the molecule. So they also illustrate the polarity or the stickiness of each compound. The more green, the less polar the compounds. It is clear that water has very little green, so it's very sticky, very polar compound. This is why its volatility is strongly changed with respect to what it should be regarding to the bulkiness of the water, as we can see now in the new scale. So, as we can see on this new scale, the two products are in the middle of the two reactants. So if we consider a distillation column as a separation method in order to obtain the purified IPAC, we can see clearly that the isopropyl alcohol will also be removed as well as the IPAC. In fact, if the distillation column is designed properly, we can see that we can separate very nicely the acetic acid from the three other compounds, which are very similar volatilities. So now, at the top of the column, we obtain a mixture with the leftover reactant, the isopropyl alcohol, and the two products, IPAC and water. Our goal is to obtain IPAC for commercial use. However, as we can see, this separation is not enough to obtain the desired purity. How can we do to separate the IPAC from the two other components, water and isopropyl alcohol? Let's analyze what's happening in the top stream. Indeed, in the top mixture, when it's condensed, we don't find one but two different liquid phases. How can this be?
This is because of chemical affinity. But after all, what is chemical affinity? Chemical affinity is an inherent resemblance between molecules. As an example, if we imagine that we have a group of 3 people composed by isopropyl alcohol, isopropyl acetate and water, and we already know that isopropyl acetate and isopropyl alcohol are very good friends because of their moderate polarity, and we know that water is a very polar molecule, it would be difficult to mix these 3 people because they don't want to stay together. As a result, we will have 2 groups. The first one composed by isopropyl acetate and isopropyl alcohol, very less sticky molecules, and the second group will be composed only by water, a very polar and sticky molecule. In fact, water is a very peculiar molecule because in liquid phase it tends to form hydrogen bonds with its neighbors. And if a molecule wants to go through this network, it must be able to form hydrogen bonds with water. Isopropyl acetate cannot do that, but isopropyl alcohol can do it, but in a moderate way. So that's the reason because they cannot stay together or they cannot mix. For example, if we mix oil and water in a glass, we will observe 2 phases. The first one, the lightest, composed by oil at the top, and the second one, the heaviest, composed by water at the bottom. So we can apply this concept to our process to separate the 2 phases already formed. But how can we do that? First, we have to take the top product of our reactive distillation and we condense it. As a result, we will have 2 phases. At the top, the lightest composed by isopropyl acetate and isopropyl alcohol, and at the bottom we will have water. And these 2 phases are separated due to its density. So the remaining phase, the organic phase composed by isopropyl alcohol and isopropyl acetate, these 2 compounds have big differences in its volatilities and we can use these differences, this property, to separate them to produce highly purified isopropyl acetate. Now we will have a full look of the isopropyl acetate process considering all the previous steps, from the synthesis, its separation from other compounds, and the industrial process. So the industrial process starts with a stream composed of all the reactants enter into the reactive distillation column, where the reaction takes place while some products are removed at the same time. Next, the top product of the reactive distillation column is condensed and the 2 phases formed are separated in a decanter, where the bottom product, composed by water, is removed and sent to a treatment elsewhere, and the remaining organic phase composed by isopropyl acetate and isopropyl alcohol is split in 2 streams. The first one is sent to the reactive distillation column as a reflux in order to reinject all the isopropyl alcohol that didn't react, and the second stream is sent to a stripping column where isopropyl alcohol is separated in order to obtain highly purified isopropyl acetate.
In this video, we have seen how two molecular features impact the way chemicals can be separated: bulkiness and stickiness. The combination of these two molecular features result in different volatilities and different affinities. In turn, they will allow the chemical engineer to design, for example, distillation columns or decantum drums. In order to design this chemical process, mathematical tools need to be used.
This is the purpose of thermodynamic models. The most recent models can take into account both bulkiness and stickiness based on the molecular structures. But there is still a long way to go for improving the productivity and accuracy that is needed for simulating such complex processes. This is the objective of the research performed in IFPEN with a chair on thermodynamics for biofuels. We hope that you enjoyed the video and that you have understood the most important thermodynamics for solving the real-life problems in industry.